Next page. What you see is the structure of ATP. All right. And there's a couple things. The usual deal. You'll never need to know that structure, all right? But it's important for understanding what's going on. If you look at the two of these things, there's all this stuff, bunch of rings, and as we learn about the structure of DNA and RNA, you'll see this actually turns out to be very similar to some molecules in RNA. In any case, the main thing is there's this blob called adenosine, and in ATP it has 3 of these P's on it, and ADP has 2 of those P's on it. So we can talk about why that matters in a second, but nomenclature, ATP is adenosine triphosphate. So that's adenosine, that's that part, 3 phosphates in a row, all right? Here is adenosine ADP, D for di, adenosine diphosphate, 2 phosphate groups. And PI is inorganic phosphate. Why is it called inorganic? Because it's not bonded to any carbon-containing molecules. So basically the difference between these two is whether that phosphate is attached on or not. So it's attached on here. So you guys, if I can hear you talking, then for sure you're driving everybody around you crazy. And I can definitely hear you talking. So, thank you. So let me explain some of this terminology here. There's a couple of different things. So ATP, and that's the tri is 3 phosphates, and ADP, di, is 2 phosphates, all right? And then this is the extra phosphate is over here. A couple of things. When I first learned about this, ATP, when they first taught me about this, they called this an energy, sorry, let me slide this down a little bit, carrier. All right? When I was in high school. And I remember thinking, how on earth do you carry energy, right? And so what I want to talk about right now is how that actually works. And we can, in fact, understand that given what we know about delta G and bonds and things like that, you can explain what it means for a molecule to carry energy. What it is, in a sense, is like a battery that has a high energy form charged up and a low energy form, the discharge form. So it turns out there's a couple things about this. This is an energy carrier, it turns out, for all living things. ATP evolved very early in evolution. And the reaction ATP going to ADP plus phosphate is delta G is about -12 kilocalories per mole. Depends on how you measure it, but that's about right. So it's very spontaneous. Therefore, releases a lot of energy to make delta G positive reactions go. All right? So the other way to look at it, so it's got a lot of energy in it. It has the energy carrier. This form is like the charged up. So ATP is the charged up form, and this is the discharge. ADP is a discharge form. All right, so how is this possible? How can these two molecules have this big difference in energy? What's going on here, right? Like the clicker question said, if you think about it simply, going from ATP to ADP, you're breaking a bond. Breaking a bond is always delta G plus. So that seems a little bit weird. Going from here to here, you're breaking a bond. Shouldn't that be delta G plus when, in fact, I'm telling you it's delta G negative? Why is that? Because in any real chemical reaction, you never just break a bond or make a bond, with some very rare exceptions. For the most part, what you're doing is swapping. You break one and you make a new one. So the answer is, what happens is you break, this bond is super weak, and you break that and replace it with this one, which is much stronger, actually with a pair of bonds which are significantly stronger. Why is that bond weak? It's hard to see up there, but those are 3 negative charges. What are they going to do? What are those negative charges going to do to one another? They repel each other, big time, right? So it's a full negative charge, and they're packed in close. They do not want to be bonded. So those 2 negative charges repel each other, as do those, and they stretch out that bond and make it significantly weaker. So it's easy to break. Here, these bonds are much stronger for a variety of reasons that you'll understand when you take organic chemistry. So the idea is you're swapping a weak bond for a strong bond. So this is negative delta G. So the other thing is, by cramming the phosphate on, you can store energy. Or by taking the phosphate off, you can get energy out. So that's how it's an energy carrier. It has two forms, and it's easy to change from one to the other. And the chemical reaction, removing that phosphate, is pretty simple. So lots of reaction cells have hijacked this to use it as a way to get energy to do particular reactions. Questions so far? Yeah. Levi. Oh, yeah, okay. So how is ATP with 3 phosphates different from 2 plus 1? The major difference is there's no covalent bond there anymore. So these are 2 free agents, now 2 molecules. And that's true. That sounds trivial, and it is. The main difference is you've broken that bond and replaced it with that weak bond and replaced it with 2 stronger bonds. So now you have 2 free agents, and they are much more stable than that thing because they don't have nearly as much of that minus charge repulsion going on. So it's because that's 1 molecule and that's 2, and so you've let these negative charges go apart from one another effectively, and that makes that's energetically favored. Other questions? Yeah. Yes. All right. So here's it. So that's a very good question. If it's a spontaneous reaction, shouldn't it degrade very quickly? That's a very important thing to keep straight. It's a spontaneous reaction, so it will happen. But the rate does not depend on delta G. The rate depends on the activation energy. And so the clever thing about ATP is, yes, absolutely, it would love to break down. But it turns out the activation energy for breaking that bond is relatively high. So ATP will break down slowly on its own, but it's not a bad storage thing. It's like a battery that will run dry if you leave it sit too long. But for the most part, it keeps it long enough to be useful. But that's, even though delta G is very negative, that doesn't mean it will happen fast. Like TNT for example, exploding has a very large negative delta G, big time spontaneous reaction. You can sit there, old unexploded bombs from World War II that have been there 70 years and haven't gone off. So the rate and the overall energy change are 2 different things. Other questions?